Hello. Before we begin, I need you to stop here and go listen to Norman Wildberger's video lecture on Mesopotamian Mathematics. Links are in the description. When you are done listening, then come on back and we will begin. Welcome back. I'm going to jump right in and present one of my solutions to the Collatz Conjecture. Now, normally I would save the presentation of this solution for the end of the video as a grand finale. But this particular solution to the Collatz Conjecture is so simple that its presentation at such a late point in the video would be almost anticlimactic. The following proof is a margin proof I created specifically for this video. And so without further ado, I now present my margin proof of the Collatz Conjecture. The key to solving the Collatz Conjecture is the realization that the Collatz process is a process that creates a collection of Fermatian derivatives. The sum of a collection of Fermatian derivatives is a Fermatian integral, and a Fermatian integral always sums to 1. I will append several solutions to the end of the video. Again, the reference numbers for equations and theorems are from the book and will most likely not match those in the appended notes. Now, despite the simplicity of this margin proof of the Collatz Conjecture, it nevertheless provides us with a nice introduction to the awesome power of the quaternion operator I and the unit fraction. The ancient Babylonians were one of the first cultures to develop trigonometry. However, their trigonometry was vastly different from that of the modern era. It has been called angleless, since there is no recorded concept of sine and cosine. But there was a concept of what we would call the run over rise. The Babylonians called this ratio the ukulu. In modern era mathematics, within the unit circle, the unit radius forms the hypotenuse of a right triangle whose sides are the sine and cosine. Any one of the three sides may be computed using the Pythagorean theorem. In the unit circle, the radius always maintains a constant length of 1. Its angle of inclination theta is directly computed from the ratio of sine theta to cosine theta, which is the tangent or the rise over run. Therefore, the equivalent of the ukulu is the contemporary cotangent. Conversely, the Babylonians made the height of such a right triangle the unit side and varied the lengths of the hypotenuse and the base, dispensing with the use of the unit circle. To compute the length of any of the three sides, they used a base 60 sexagesimal number system coupled with their version of the Pythagorean theorem called the diagonal rule. By using only divisors of regular numbers, that is, numbers that evenly divide 60, they were able to compute the size of a right triangle by using the exact ratio of the sides. Western mathematical scholars have debated whether or not this should actually be classified as trigonometry, because trigonometry as they know it, that is, angle trigonometry, was discovered well after the Babylonians. Drawing upon the Quaternion principle that calculus is trigonometry, it is clear that this Babylonian process was not trigonometry in the sense Western scholars have interpreted the discipline, but was rather the first systematic use of differential calculus. The exact ratio of two sides of a right triangle is by definition a derivative. The Babylonians used the relationship beta over 1 equals ukulu beta equals run over rise, which is equivalent to the cotangent. And sure enough, this relationship is verified by the trig chart, which in turn verifies that the ukulu is indeed a derivative. Wildberger and Mansfield have named this 60-base Babylonian system of trigonometry Babylonian exact sexagesimal trigonometry, or BESS. This is just a Babylonian expression of the scalar expression of quick. Therefore, we should more properly express BESS as BESC, that is, Babylonian exact sexagesimal calculus, or BES quick, Babylonian exact sexagesimal quick. Best has been interpreted as dispensing with the use of angles and thus ostensibly dispensing with the use of the unit circle, and thus dispensing with the use of Euler's formula. This may of course be the practical outcome of the Babylonians' use of best, but it is certainly not the case mathematically. Best simply utilizes the scalar form of Euler's formula and Johnson's theorem. It essentially tracks the progress of the oscillating C's in the Quickian continuity equation by tethering the varying sagitta or Euclid or secant or cosine to a stationary I sign of constant 1. Babylonian calculus confirms that quaternion algebra in general and Quickian mathematics in particular work just as well in a square or rectangle as it does in the unit circle. This must be the case since both the square and the circle contain 360 degrees or 2 pi radians, which again confirms that the rules of quaternions are valid within all conic sections and platonic solids. In addition to being well versed in the use and application of proper and improper fractions, the Kemetians also employed a system of unit fractions, that is, fractions with a constant numerator of 1. In this system, no two unit fraction addends were allowed to be the same. Rather than 1/3 plus 1/3 equals 2/3, they would compute 1/2 plus 1/6 equals 2/3. Each addend was distinct and unique. They found that any unit fraction could be expressed as the sum of some two other unit fractions by this formula. 1 over q equals 1 over q plus 1 over q times q plus 1. Given this formula, let's take another look at best. We have established that in best, the Babylonians used a relationship beta over 1 equals Euclid beta equals run over rise, which is equivalent to the cotangent. The equivalent of the Babylonian Euclid is the Egyptian secant. Therefore, we may substitute the Euclid with the secant, yielding the following. Beta over 1 equals secant beta equals run over rise, which is equivalent to the cotangent. Both Quick and Newtonian calculus conventionally uses the tangent as the derivative or limit, even though in Quick we may use any of the trig identities to represent a derivative. Suppose, however, that the Egyptians decided to create their own system of calculus, opting to use the same convention of allowing the tangent to represent a derivative. It is given that the secant as cotangent is the reciprocal of the tangent. If the tangent is to serve as the derivative, then the cotangent must act as the integral. Taking the reciprocal of the cotangent yields the following. 1 over beta equals negative secant beta equals negative run over rise, which is equivalent to negative cotangent, which is equivalent to rise over run, which is equivalent to the tangent. Since 1 over beta is a unit fraction, then it is a simple matter to equate 1 over beta with 1 over q. Therefore, 1 over beta equals 1 over q equals 1 over q plus 1 over q times q plus 1, which equals the tangent. A unit fraction is also known as an Egyptian unit fraction. This by definition renders each Egyptian unit fraction a unit quaternion and therefore a derivative. But Kemetians took this a step further. They said, wait a minute, even though beta might be a sexagesimal regular number to the Babylonian, who says q has to be sexagesimal to us? The equation says that q need only be an integer, any integer. If we always make q an integer, then we will always get some unit fraction or denominator that is always comprised of an integer, which means we don't ever have to deal with any type of irrationality in this unit fraction system. And if we do that, we will always get a unique fraction that can always be split into two other unit fractions, which is precisely what Euler's formula demands. The Babylonian system of calculus was restricted to the use of regular numbers, that is, integers that are evenly divisible into 60s, such as 2, 3, or 5. Though the calculations were impressive and the differentiation exact, the discipline was stilted by this natural number restriction. This ushered in the discovery of the Kemetian system of differential calculus through the use of unit fractions. The Kemetians were well versed in the use and calculations of proper and improper fractions. There was no reason why they would pursue the use of unit fractions with such zeal and rigor unless it was actually used for some other special mathematical purpose. This special purpose turns out to be a form of QATROAO, that is, a form of calculus based upon the quaternion, which in turn was used to build the pyramids. This evolved Kemetian system of unit fraction-based QATROAO proves to be far superior to best in that it accepts any integer as a divisor in its system. Its answer or resulting derivative is always exact and always rational. To demonstrate how the Egyptians may have used this unit fraction-based system of calculus, consider the following example. Given 13 pies to be evenly distributed among 12 siblings, what is the smallest slice allowable? That is, what is the minima? Only 3 slicing schemes are allowed. To solve, 6 pies are cut into halves, 4 into thirds, and the remaining 3 into quarters. Therefore, f prime of x equals f prime of 13 over 12 equals 1/4. The Egyptian equivalent of the ukulu is the secant. Both are negative tangents. Thus, both are equivalent to the angle of inclination of the secant. Both trace out a finite but unique arc length along the unit circle, and thus both are by definition quaternions. But the ukulu and secant were supposedly interpreted as being angleless. Thus, for both Babylonian and Kemetian calculus, calculations were made along the base or cosine or sagitta, thus bypassing any direct angular considerations. Computationally, the Babylonians employed the diagonal rule of secants, and their version of Euclid's formula to produce families of diagonal triples. Indeed, what we see from the hypotenusis of these triples is that they are variations of the secant, as the sagitta matriculates along the base while allowing the I sign to maintain a constant value of 1. Their interpretation of Euclid's formula, expressed in terms of the diagonal rule, is as follows. The Babylonians used a reciprocal table to find suitable values for x and the reciprocal of x. But trigonometrically, the reciprocal of x as cosine is the secant, which is what they were looking for in the first place. The Kemetians simply and cleverly dispensed with x as base in the Babylonians' interpretation of Euclid's formula. They replaced this equation with their equivalent unit fraction formula, replacing the Babylonian reciprocal 1 over x with their unit fraction 1 over q. This effectively freed their computations from the limitations of regular numbers and placed it firmly within the mathematical architecture of QATROAO. That is, as 1 over q plus 1, which is equivalent to the sagitta, goes to 0, then 1 over q plus 1, which is equivalent to the cosine, goes to 1. Therefore, I equals jk, which is equivalent to j plus k, equals 1 over q equals 0 plus 1 over q times 1, thus yielding a true fundamental statement in terms of QATROAO. The Egyptian unit fraction is 1 over run. The Babylonian ukulu and the Egyptian secant are both run over 1. Thus the Babylonian ukulu and the Egyptian secant are both the reciprocal of the Egyptian unit fraction. Both are unit fraction integrals that produced integers. Thus any and every angle measure was an exact, precise measurement. In truth, this method is far superior to the Newtonian concept of limits and rivals that of the Quaternion model. Where the Egyptians used unit fractions as their derivatives, QATROAO uses Gaussian integers. Gaussian integers are square roots of integers. QATROAO sums Gaussian integers as integers to obtain a precise integer sum, where the Kemetians take the reciprocal of the unit fraction and sum the resulting integers to form a precise integer sum. Rational trigonometry, Kemetian calculus, and QATROAO may all obviate irrationality. Thus the Kemetian fundamental theorem of calculus states that the secant as integral is the reciprocal of the unit fraction as derivative. One may say, since the Kemetians came up with unit fraction calculus first, then perhaps I should rename QUIC to be QKC, Quaternion Kemetian Calculus. And as much as I admire the sheer brilliance and mathematical sophistication of both the Kemetian and Babylonian systems, those systems still form but a subset of QUIC. QUIC is a much more expansive and versatile and fungible system. BEST and the Kemetian system of unit fraction calculus are but two of the myriad of systems that operate under the QUICian umbrella. Previously, it was demonstrated that the Babylonians used the relationship beta over 1 equals Euclidean beta equals run over i's, which is equivalent to the cotangent. And sure enough, this relationship is verified by the trig chart, which in turn verifies that the Euclidean is indeed a derivative. Therefore, beta over delta equals 1. Therefore, beta equals delta, which again is verified by the trigonometric diagram. Now, what these two equations are actually telling us is that in a diagonal triple, if we allow one side to maintain a constant length of 1, we may generate a family of diagonal triples where each of the respective resulting hypotenuses is equal to each of the respective resulting non-unit sides, which again is verified by the trigonometric diagram. And again we say, if Euler's formula says that all trigonometric identities are equivalent, then Euler's formula means it. If Euler's formula says that the long side of a diagonal triple is equal to, not just equivalent to, but is equal to the hypotenuse, then Euler's formula means it. And no better example of this trigonometric relationship is that exemplified by the orthogonal relationship demonstrated in a set of spiraling right triangles. QUIC finds that an even more compact, elegant form of the Kemetian system of differentiation is displayed through the spiraling of a set of spiraling diagonal triples. In this system, rather than allowing the long side to maintain a constant value of 1, we instead allow the base to maintain a constant value of 1. By Quickian principles, at the ICR, the integral, that is the long side, and the derivative, that is the hypotenuse, become indistinguishable. Thus, in this spiraling set of diagonal triples, every side, other than the base, is both simultaneously long side and hypotenuse. If we square all sides of all triples, then every side is an integer, and every ratio is rational. And if we elect to take the conjugate of all these integer sides, then every side can be expressed as a unit fraction or a Gaussian integer. Baker states the following. Alternatively, we may express Baker's segmentation reversal equation as follows. Cube root of -1 equals 1/2 plus the square root of 3 over 2, which is equal to 1/2 times 1 plus the square root of 3, which is equivalent to -I times 1 plus the square root of 3, which is equivalent to 1 plus the square root of 3 to the power of -I. And so in general, we may state that if we are to break up reversal into n number of steps, then we may apply the formula 1 plus the square root of n to the -I. Alternatively, we may express Baker's segmentation reversal equation in terms of Gaussian integers, yielding the quantity 1 plus the square root of n to the power of -I is equal to the quantity square root of 1 plus the square root of n to the power of -I. And we see that this Gaussian form of the equation may be slightly altered to yield an exact formulation for the spiraling of right triangles. We allow the base to be the Gaussian integer e is equal to the square root of 1, which is equivalent to 1, and -I is equal to the unit quaternion. The unit quaternion acts on e, precessing e a distance of pi over 2 radians n times. Therefore, as Gaussian integers, we obtain the following. The quantity 1 plus the square root of n to the -I is equal to the quantity the square root of 1 plus the square root of n to the power negative I, which is equal to the square root of 1 plus n. This equation says that if we add a short side of square root of 1 perpendicularly to a long side of square root of n, we simultaneously obtain both a hypotenuse of length square root of 1 plus n and a long side of the same length of a succeeding diagonal triple whose hypotenuse measures the square root of 1 plus the quantity 1 plus n. As integers, we may also obtain the quadrants, which is given as follows. Therefore, in the set of spiraling right triangles, we may state the following. Every hypotenuse of each diagonal triple is simply the arithmetic sum of the long side of that diagonal triple plus 1. Every long side is the hypotenuse of the preceding diagonal triple. Every integer is a quaternion, and therefore every integer, Gaussian or otherwise, is a quantum of precession. Spiraling of the integers is not coincidental or happenstance. It is a consequence of every quaternion being in a state of constant precession, since every integer is a quantum of precession. Now, even though I presented proof of the Collatz conjecture at the beginning of the video, I will still end this video with another proof of the conjecture. This proof will be based upon Ethiopian multiplication. Ethiopian multiplication is a method of multiplying integers using only addition, doubling, and halving. Take any two integer factors and list them at the top of two columns. In the left column, repeatedly halve the last number, discarding any division remainders, and write the result below the last in the same column until a value of 1 is obtained. In the right column, repeatedly double the last number and write the result below until the final entry is in the same row as 1. Discard any row where the value in the left column is even. Sum the values in the right-hand column. This yields the desired product. Ethiopian multiplication very succinctly and elegantly proves the Collatz conjecture. Continual halving of integers always produces 1. It also establishes the utility of using Fermatian derivatives and integrals to form limits of 0.